Okay, good morning, everybody, and welcome to this forum, Shaleology, which is about shale gas, of course, and it's supported by the Horizon 2020 Forum, SXT, Shale X Environment, which is an excellent example of collaboration between research from academic and in other institutions, industry across Europe. I'd just like to say at the start that, well, there are some housekeeping things that are going past on the sign here related to the Geological Society and fire and safety, so you should look at those. There is an extra exit on the side here, as well as the ones at the back. And those of you who've not been here before, the deep rumbling sound you hear from time to time is the underground. Okay, the train's going past quite close vertically to where we are. So first of all, a couple of thanks. Thanks to the Geological Society for hosting us, and in particular the previous head of the Geological Society here, Edmund Nicholas, who suggested to us that we hold a forum here from time to time to help explain about shale gas and using this wonderful location for that purpose in London. So thanks to him. Thanks also to Evgenia and Pauline for doing the organisation of the logistics behind the scenes from the European office at UCL. And just a little bit of introduction, the Shale X Environment Consortium consists of more than 10 partners across Europe, and it's driven by Alberto Striolo, who's going to tell you something about SXT as the first talk and introduction to the topic of where we're coming from. But my hope is today that you will hear new information, you'll learn a lot about what's happening. In the afternoon, you'll have noticed there is a panel discussion, which is a free format. So feel free to think of questions during the morning that you might want to ask of those people this afternoon. You don't have to ask questions, but that and the entire procedure are being recorded. We will have a right of veto in January, what we want to do with that recording and different parts of it. But that just means that if you have a question to ask, please wait until you get a microphone to ask a question. And might I suggest that it would be useful if you could just briefly say who you are when you ask the question in the audience before you ask your question for any of the speakers or the panel this afternoon or the other talks. As Al mentioned to me, it's probably useful that people have their mobile phones turned off since this will be recorded, so that would be embarrassing to have you on there as a focal point. And with that, I'd like to invite the first speaker, which is Professor Alberto Striolo from University College London Chemical Engineering, to come and explain to us what SXT is.
Thank you, Adrian. Let me start by thanking Adrian for putting this all together. I admit that I really didn't do much for this, so thank you very much, Adrian. And of course, thanks Genia and Pauline for doing all the administration, and thanks to the Geological Society for hosting us the day before Christmas, pretty much. So what I decided to do here was to give just a little bit of an overview about what SXT is trying to do and what the people that are involved with the projects are accomplishing. And many of these people are showing posters next room, so the whole point of this forum is to stimulate discussions so that we can transfer what we are doing and we can learn from your comments and try to do things better if needs be. I should probably make a little bit of a correction. These, both Adrian and I are coordinating these activities, not just me, Adrian. So yeah, thanks for your help in all of this. So here we are. So Adrian mentioned we do have a large number of partners. So those are the symbols from all of them. And I would like to point out that each one of those partners is essential for the success of the project. I'm the one speaking here, so I need to make a disclaimer. I hope that what I will try to convey reflects what is the work that has been done, but the conclusions are only mine, of course, and I hope I really don't mess up too much. But anyways, this is the summary of what we proposed to the European Commission now 2 years ago. Essentially, at the time, we were recognizing that shale gas could be an opportunity for Europe and the UK in particular, but there are a number of challenges that need to be addressed. In particular, as far as we know, we are only producing 15% of the gas in place in the North American shale formations, so perhaps we need to learn how to produce more of that. And the environmental impact of the technology is not quite well understood. So if we want to contribute to this technology, perhaps we should target these challenges and try to make a contribution to it, which is what we are setting about to do. The way we proposed to tackle these challenges is summarized in this cartoon over here. This is sort of a workflow that we proposed. And essentially what we say is that, well, if we want to get a feeling about what is the environmental impact of the technology, we need to be able to access rock samples from specific formations. We need to study those rock samples. We need to understand the behavior of the fluids in those rock samples. From these fundamental studies, we should be able to estimate how much of the gas we can produce. And at the same time, we should be able to estimate what will be the environmental impact connected with the production of that gas. And then all we can do from an academic point of view is to provide the lawmakers with both estimates, what is the expected benefit, the economic benefit, and what is the expected environmental impact. And we would like to estimate that with that ratio worthiness, W, and at that point it will be the lawmakers' job to decide on what to do, and that decision should be taken in coordination with all stakeholders. So what I'll do in the next few minutes, I don't have the green light here. Maybe my time is already over. But what I'll do, I'll walk you through what we are doing in each one of these steps, and I will highlight the partners that are actually doing the various activities. So the first is accessing shale rock samples. As we know, after 2014, the production of shale gas in Europe has kind of not progressed very fast. So it has been not easy to access rock samples, but the British Geological Survey had stored the rock samples from the pre-Sol 1. And so we have been lucky enough to be able to access those rock samples. These are some images. So this will be the depth of the samples, and this is the sample number. And we have been able to access some of those rock samples. Those are, most of the science that we do is based on the Boland Formation at this point. But we are also lucky enough that, we do have access to other samples, some from a repository that was supported by the British Gas Group, now Shell, and some were given to us from basically operators that are interested in understanding better what is the properties of their operations. So what we do now that we have the samples? Well, in Manchester, our colleagues are characterizing these rock samples. This is just a cartoon. We will learn more during the day. And when I present these, I like to point out that in only 3 millimeters over here, the chemical properties of these rocks change quite dramatically. And you can see, for example, this is the organic content. It goes from 0 to perhaps a few, maybe even 10% in some very narrow regions. What I point out here usually is that the clay content that we get from our analysis tends to be very low. So what Niels is doing at UCL is also putting together information from different sources in this part of the slide over here. And this helps us understand a little better the Boland Formation in general. But I point out here that the clay content remains a little bit challenging. Our measurements tell us that there is not much clay in those samples. But if we look at the literature, they tell us that there is a significant amount of clay. Perhaps those literature analyses came from different formations, different sites nearby. Perhaps the techniques that were used to characterize those samples were different, and we are trying to solve these discrepancies. At UCL, our colleagues in earth sciences are measuring permeabilities in 2 directions. These are data from commercial samples, and that's why I don't give you the exact numbers. But the point is that the permeability is very low, but it can be a couple of orders of magnitude difference depending on the direction along which you measure those permeabilities. And now we are trying to understand those permeability results by taking a look at what is the pore network within those rocks. And I believe Niels is going to give us an overview about all of this progress. In Germany, at Potsdam, we are measuring mechanical properties of the various rock samples. So this one here is a sample from the Boland. So this is a stress-strain type curve. This is the Boland, this is a Barnett, this is a Marcellus. So those are two American shales compared to the Boland. They have similar properties in terms of stress-strain. These are the German rocks, and they tend to be very ductile. So from this analysis, what we can conclude is that the Boland is actually relatively easy to frack. But the German, the Posidonia one, is actually quite difficult to frack. They are now doing some experiments that include creep to understand what is the effect of temperature on these results. And we are trying to quantify this characterization based on the properties of the rock. And so that we will be able to understand, just by knowing what is the rock chemical composition, what will be the tendency of that rock to frack or not frack. Okay, this is kind of a summary about the experimental characterization of the rock samples. And from this analysis, as I mentioned earlier, what we need to do is to try to predict what is the fluid properties inside of these rocks. This is quite a challenging problem, as I like it over here by Tobias. He prepared this very nice slide. Basically, we can characterize the rock samples at very high resolution, a single pore type of analysis. But what we really need is to be able to predict how the fluid transport in fractures that are created inside of these rocks. That's a multi-scale problem. It's not easy to solve. There is not a clear answer out there. So we are trying to make our contribution there. And I will walk through a few of the contributions that we are trying to make there. At the single pore level, so one single pore, very small dimensions of 1-2 nanometers, we are using molecular simulations to try to understand the behavior of the fluids. We have one poster by Yang outside that is summarizing these activities. What I point out is the difference between these two graphs. So this one here, this is the solubility of salt, sodium chloride, in water, when that water is confined within a pore, and that pore has different widths, from 2.5 nanometers down to 1 nanometer. And this solubility is normalized by the solubility of salt in bulk water. So up here, 1 will be the solubility of salt in water that we measure experimentally on bulk water every day when we cook pasta. I'm Italian, as you can tell. Well, as you make the pores smaller and smaller, what happens is that the solubility of salt goes down. So it tends to form crystals inside of the pores. This is the opposite. This is the solubility of methane inside of water when water is confined inside of a small pore. And these are results in one specific pore of 1 nanometer in dimension, and this is the bulk pressure. These points here are the solubilities of methanes in bulk water. So in this case, what you see is that we have 1 or 2 orders of magnitude larger solubility of methane in water when the water is confined in a very small pore. So we have very different behaviors, higher solubility of methane, lower solubility of the salts. And we need to understand what that means in terms of producing that gas and reducing the environmental impact of producing that gas. Here, we are trying to go from that single-level pore to bigger scales. This is still at the preliminary stages. These are simulations that Anne conducted for a pore, and she's trying to understand what type of gas go through a pore that is filled with water. Turns out that hydrogen sulfide goes through that pore much faster than methane or ethane. We need to understand how that correlates with the productivity of methane versus other hydrocarbons from shale formations. This doesn't work now, but it is an attempt by Maria. She also has a poster out there to use other sort of techniques. It's called kinetic Monte Carlo, to try to understand what happens when we have a number of pores that are connected with each other. And that's an analytical approach that tries to, again, predict what will be the behavior of a number of pores that are connected to tell us what is the permeability of a rock that contains all of those pores. If we do manage to make some progress along these lines, we will be able to connect with the work that Tobias is doing in Germany. These are results from Geological. This is basically a rock in which we have put a few fractures in there. And what we are doing, basically, we are saying, OK, there is fluid over here at large pressure. we are looking at how that fluid propagates in the rock, and we are also looking at the propagation of the stresses that are connected with the propagation of the fluid. So far, the fractures are fixed, they're not moving. The idea will be now to include information about the rock mechanical properties and the permeabilities of the matrix so that we can better understand how this propagation of the pressure field propagates the fractures that are present in the rock. We'll see where we go. Hopefully, we will go a little bit further. To validate, we are collaborating with a group in the Czech Republic, and they are making materials that are zeolites that have a very controlled pore size distribution, and in principle, we can use those materials in the lab to do very specific experiments to see that our theoretical calculations make some sense. Still progress to be done there, but we have set the foundations to make it happen. Now, I changed gears a little bit. This is work conducted in Florence, and we have 3 people from the University of Florence over there, led by Moira. And the goal over there is to try to make fracturing fluids that lower the environmental impact of the technology. And the way to do it, in our opinion, is to make sure that these fluids work no matter what the salt content is. So here, I show you the viscosity as a function of the shear stress. And I think there are 2 posters out there that summarize more of these results. So these are viscosity as a shear stress. And this one in green is guar gum, 1% in water. The other 3 colors are the same guar gum 1% in water, but they added some salt, the same amount of salt, but 3 different types. And what you see is that the viscosity changes by more than 1 order of magnitude simply by changing the type of the salt. Now, different rock formations have different salts present in them, and as a consequence, it is possible that if we don't know exactly what are the properties of the rocks, we will not be able to use appropriately the fracturing fluid to disperse the propellants. That's where we are trying to make some contributions over here. Now, depending on what fracturing fluids we use and what type of additives we use, the properties of the flowback water and the produced water will probably change as well. The group in Alicante is trying to say, okay, what do we do with that flowback water? The principle is that in Europe, most likely we will not be able to re-inject the water because of the induced seismicity problems that have been observed in Oklahoma, for example. So if we don't re-inject it, we will probably have to treat it. So their activity is to try to identify what is the most economical and best way to actually treat that water and to be able to separate the chemicals and the salt that we don't want to disperse the environment. They actually have a couple of papers already out there, and we'll see where this goes. Now, we can try to put all of these together, but we also need a little bit of risk assessment. The risks, we haven't really started to do much over here, but the risks that we are trying to consider are the induced seismicity. To make contributions here, we are actually collaborating with the other European-funded projects because they have much more experience on these subjects than we do. And we are also looking at the possibility of having a well that ends up bursting. Still some work to be done over here, but the results from these will tell us how far from a community the various wells should be to make sure that there is no significant accident. Okay. Now, in principle, once we conclude all of these activities, we should be able to condense and have a feeling about what is the environmental impact of the technology over the life cycle of the application of the technology in a single well. To do that, we are using the expertise from Carla, who's sitting on the back, and basically this is a life cycle approach. We take into consideration all the energies, all the efforts that go into drilling the well, fracturing the well, producing the gas, cleaning up the gas, distributing the gas, and so on and so forth. And this analysis has been done, I think it's now published, for the delivery of 1 megajoules of natural gas to the end consumer. And we can compare these results to what is the environmental impact of the natural gas that we use here in the UK, because we can use the literature values for that. So this column over here will be the contribution of CO2 equivalent emissions that we actually contribute whenever we use natural gas in our own home. And what we see from this analysis is that the hypothetical shale gas in the UK, in some cases, can actually have a lower CO2 emissions compared to the current case, but in other cases it can have a comparable or even larger contribution. So this type of analysis is going to tell us, okay, this is the best way to actually produce the gas, and it's going to tell us what are the best practices to make sure that the environmental impact is lower. And this is a kind of a toy analysis. We were looking at the amount of fresh water that could be used, that should be used to produce 1 natural gas of gas from the Boland Formation. These are very preliminary results. And here what we did was to assume different permeabilities of the rock. And basically what you see is that the lower the permeability, the larger is going to be the amount of fresh water that you use to produce 1 megajoule of natural gas. And the point is that the lower the permeability, the less amount of gas you actually produce, everything else being equal, and as a consequence, the environmental impact is going to be larger. So basically the message is, if we learn to produce more gas in a smart way, we may actually be able to lower the environmental impact of the technology. With this, I'm pretty sure I am over my time, but we do have a number of activities, including a master's program, Global Management of Natural Resources. We actually have 4 of the first students here in the room. Raise your hand. And these are very talented students, so if you guys are interested in learning what the new generation is thinking about producing gas and working with natural resources, here they are. At this point, I should probably shut up, and thanks again for coming, and let's hope this is going to be a productive day.
Do you want a question? Are there any questions from this opening stage? Well, there'll be chances for questions again later, but was there a question for anybody? No? No. You escaped. Thank you very much. That was an excellent overview and introduction to the whole of the SXT program. So, trying to keep close to time, I'd like to move to the next talk, UK Geological Perspective of Energy Reserves by David Schofield. Who's here? Didn't realise you were sitting right behind me.
Thanks.
That's my walk to the office right there.
Oh, great. Morning, everybody. The invite for this talk originally went out to my boss, Mike Stevenson. Couldn't make it today, so instead you've got me. I'm BGS's incoming director for energy systems and basin analysis. I'm still learning the ropes. I don't specifically have a background in shale gas, so if I can't answer your questions, I'll make sure that you get in touch with somebody who can. What I wanted to do before I really started was sort of frame the problem that we would see it from a BGS perspective. So most of our research is really focused on applied solutions, mostly that support the public sector. That's what our long, nearly 200-year history is. And this slide sort of quite nicely encapsulates one of the views that you could have about shale. So the coloured polygons on this map of the north of England show you the potential resource areas that come from our 2013 Boland Shale resource assessment. It's obviously carboniferous, Boland Shale. It underlies carboniferous coal measures, exploitation of which drove the Industrial Revolution, industrialisation north of England. So it's no surprise that where the potential shale gas resources are reasonably coincident with some of the UK's main industrial, post-industrial conurbations and the green corridors that sort of sit between them. So that presents a problem in terms of public exposure, in terms of risk. You know, and these are questions that, as a research community, we're working hard to try and resolve in some respects. So the big question about shale gas, is it possible to do it safely and sustainably in the broadest sense? And is it possible to do that cost effectively? So those are the kind of questions, as the previous speaker suggested, are sort of frame what we're doing in many respects. So in this talk, I'm actually really just going to quickly run through what we've done to date and what we're sort of doing at the moment in BGS, what we've done in terms of resource assessments, what we're doing in terms of baseline monitoring, a few bits of research that we're doing which overlap somewhat with things that this community is doing. And there's a couple of points that are quite interesting for all of us to think about. One is communication, and the other one is independence, really. And that's something that in some respects we see ourselves in BGS, but we constantly question what that really means. And I'm going to finish off the talk with a few seconds about what we're going to do in the future. So in terms of what we've done about resource assessment, we've undertaken 3 studies on behalf of ASWA's Department of Energy. The first one was in the north of England for the Bowland Shale. The second and third ones were the Jurassic of the Weald in the south of England, of which there's just been an extension to just delivered now, and the Midland Valley in Scotland. So the results of those are all out on the BGS website and the BEIS website as well, so you can see those reports. So we were effectively commissioned by them to carry out a regional scale resource assessment. The Bowland Shale one was delivered 2014. As I say, the most recent update to the Weald was just this year. Our approach was effectively to take a bottom-up approach where we built a geological model based on existing data. We looked at the volume that we'd created, so the gross volume from that, and excluded areas which we thought were less likely to be productive based on lithological evidence. We made some assumptions about gas content per unit volume, multiplied the two. Fairly straightforward, but in that you can see that there's plenty of room for improvement. And in fact, these kinds of resource assessments should probably be seen as things that need updating. So certainly, since we've worked in the Bowland Shale, there has been no new exploration, so there are no new wells and there's no new seismic data that we can look at, but the research community has learnt an awful lot about the material in the Bowland Shale because we have looked at what there is. So some of the parameters that we put in that change our gross volume to a net volume probably could now be examined again. This is an example about the constraint that actually the availability of data brings to you. This is, again, the map of the north of England. The blue squiggles are bits of seismic data. The black dots are wells. The black ones are publicly available wells or wells that are available to us in the public domain. The green ones in the west are actually still not released well data. The point about this is, as far as the UK is concerned, perhaps with the exception of the far south of England, this is probably the densest subsurface data we have in the UK. You know, its legacy of conventional petroleum exploration and coal exploration has given us a high density of data. Having said that, so this is an example of a Bowland Shale thickness, so this is from our report. You can see that there are areas which probably are underlain by Bowland Shale where we haven't completed our model. So even with that high density of UK subsurface information, it's still not great in terms of producing a really well constrained gross volume. So the hope is, as exploration proceeds, that there will be new information that helps update that understanding of distribution of the Bowland Shale. I really put that in just to give you some kind of understanding about the constraint on the work that we've done and the fact that we don't really see this as a final thing. It's more of a snapshot of what we could do at the time with the knowledge that we had, and that knowledge is constantly changing. So the second main area where we have worked is in looking at environmental baselines and monitoring. We've done this both on a national scale with partners in the regulator, so that'd be with the Environment Agency, and also local scale surveys, mostly looking at water, seismicity, ground motion, radon, water quality, those kinds of things. I'm going to put my glasses on, actually, because I can't read that. No, it is. There we go. Now I know what I'm trying. Oh, that's right, okay. I mean, and the main reason for doing this is to produce baselines that help inform regulators, shape how we actually develop regulation, shape how we develop monitoring going forward, and help inform the scientific debate. So there's a sort of multi-purpose reason for doing this. And one of the other things that comes out of it, of course, is helping to develop what sort of sensors we use. So the national surveys, what we generally refer to this as methane in groundwater. Well, in fact, it is a little bit more than that. We've actually analysed a whole range of different parameters. And what you can see on the map is effectively methane concentrations in groundwater, and it's based on Environment Agency groundwater monitoring boreholes. So that's as the baseline as it looks at the moment. It is monitoring. We go back every few months with the help and support of the Environment Agency. And the results of that get released on our web pages. So that's a kind of first introduction to the communication aspect. With this work around shale gas, there is a lot of public scrutiny. So we're actually trying to put data out into the public domain as much as we can so that science seems to be transparent. So that was one of the decisions we made quite early on to start getting actual data out into the public domain. It's my colleague Rob Ward, who's the Director of Groundwater, who manages that. Obviously, we coordinate the UK's seismic array, so we do produce statistics and information about a baseline seismicity, so that's just a snapshot from our website of earthquakes in the UK. I think this particular picture gets periodically updated, but that's really sort of the natural earthquake side. We also have a tool that we've developed looking at rock stress. I think this example is some borehole breakouts from the north of England. This is a particular, I wouldn't have said this is monitoring as such, but it's about compiling information that's out there and putting it in a format that's available for people to use and access. So there's a lot of borehole breakout information in there, but it's, I think, fairly patchy and is a work in progress. Every time a new piece of information comes in, we try and update this. So in terms of local monitoring, we have 2 projects on the go with various partners, some of whom will be represented in this room, both in the HE sector and the public sector. The 2 local monitoring in Lancashire and the Vale of Pickering, these are both around areas where there is planning applications for hydraulic fracturing granted or being considered at the moment. And the idea was that we actually carry out some monitoring in advance of these exercises happening, completely independent of the operators, to establish a baseline. Okay, some of the data that's produced is put out on our web in real time, so it's telemetered, and some of it's sort of periodically connected and updated on the web. And we're looking at water quality, ground and surface, ground motion, induced seismicity, atmospheric composition, greenhouse gases and air quality, and radon as well. So there's a number of baseline parameters that are currently being monitored. Press the right button, and nothing is happening. Okay. Oh, there we go. Now it's catching up with itself. Right. Okay, so again, coming back to where I was, apologies for that. The point about communication, again, is trying to get this material out to the public in a fairly unbiased way, and this actually means putting our data out there. So for those of us who have a background in research, actually sticking your data out in the public seems counterintuitive in many respects. We're quite used to thinking hard about it, interpreting it, writing elegant stories about it, and then giving that to the peer review environment. What we're trying to do in terms of being more transparent is actually taking our raw data and making it available for people to use. It's a sort of a direction of travel for us, but it's psychologically quite a tough one. It's a bit of a journey in terms of how we feel about that ourselves. The other thing perhaps we're doing in the environment is some risk assessment tools. Again, this is with partners in the Environment Agency. One particular piece of work that I'd highlight is looking at the relationship between potential formations which are potentially shale gas prospective and aquifers. The way that we've done this is effectively to identify aquifers and their bases, identify the tops of shale formations, and look at the separation between the two. This is one of the parameters that the Environment Agency have been looking at in terms of developing high-level regulation. The way that we did this was to take, on the top left there, which is our UK 3D fence diagram of the United Kingdom. Okay, so that is based on our 1 to 625K geological map, so that's our surface intercept. And all our available subsurface data boiled down into a series of cross-sections. That's a bit of an out-of-date snapshot of it. It's actually a denser network than that. But in doing that over several years and compiling that, what it did highlight is that our knowledge of the subsurface in terms of real data is actually quite limited. So that's quite a conceptualized geological model. So when you really get into lots of the UK, there's quite sparse subsurface data that really helps you constrain the geology in a way that we need to go forward with this kind of work. So what we've done with it, cross-section at the bottom illustrates that quite nicely. You can see bases of aquifers, this is the wheeled here, in green at the top there, so it's a nominal, I think, about 300 or 400 metres base of aquifer in chalk. That's based on European guidelines that the EA are happy with using. And the tops of some of the prospective shale units highlighted here, Kimmeridge, Oxford-Clate, Lias. So you simply process that in the model and come up with a map that shows you, top right there, the map that shows you the separation between the base of your aquifer and the top of those shale horizons. Again, based on the data that we have available. And what that shows you, the blue colours are less than 200 metres separation, and the greens and yellows are somewhat more than that. Okay. Again, that information is delivered on the web so that the public can access it, both through the BGS website and also through the Environment Agency's route. And you can look at different formations of shale, and you can look at different aquifers and get results out in that sense. Research. So a lot of the research we do sounds sort of similar flavours to the research that many of you are doing here. Just a few little snapshots of it. We're looking at fractures, and one example of that would be the work that perhaps our Edinburgh anisotropy group is doing, looking at ways of processing seismic data and interpreting seismic data to tell us something about fractures. That's a project that's been running successfully for about 30 years now, and is really just turning itself more specifically to the shale environment. We also do transport experiments, permeability, porosity experiments, and there's the obligatory bottom left picture of a steel box in a laboratory that could be doing anything as far as I'm concerned. There's probably a tap for getting coffee out of at the side, I would have thought. Also, we're doing basic geological research. I mean, most of our research, in my mind, forms into the bracket of looking at resource optimization, things that you can do to help you understand which bits of shale are perhaps more prospective and how you can access that more readily. Okay, so we are doing a lot of work in trying to understand shale facies, again, focusing largely on the Boulden Shale at the moment, as you're indeed working. So that would be properties, facies distribution, quite basic geology, really. But one example of that, bottom right, which is more interesting in some respects, is the work that we're doing on amorphous organic material, which is the majority organic material in the Boulden Shale. So we have a research group that's really looking at where is it, how's it deposited, how's it preserved, what's its distribution, and what's the link between the amorphous organic material itself and shale and gas in shale, basically. So that's a snapshot of some of the research. It's funded through our NERC national capability. It's funded through competitively won grants. It's also funded through an industry consortia. Okay, so what comes out through national capability and industry consortia is published straight away in the peer-reviewed format that you're used to. Work that we do through private sector consortium usually has an embargo attached to it. And those of you who've worked in petroleum geoscience, we're very familiar with that kind of environment. A couple of words about communication. This is a new one for us as well. Because of the public scrutiny of shale, we've had to learn about communication. Putting your data out in the public domain has been one of those lessons. Then another one is regularly talking to the public. This is an example from the, I think, either Lancashire or Vale of Pickering. We now hold regular public forums where the local stakeholders are invited along. We talk to them about what we're doing in terms that they can understand, hopefully. It's videoed. You can see it on YouTube. I think we do this 6 monthly or when there's something to report. It's quite interesting. We get the whole range of responses from these of people who are supportive and interested, people who don't understand, people who do understand a bit, people who are very strongly opinionated. But it's something that we feel that we have to do to maintain our kind of trustworthy position, really. We also have a number of vignettes that you can grab through our website on frequently asked questions about shale. I was looking at this slide the other day when I borrowed it and noticed that some of these are a bit out of date, which actually is another thing that you learn about communication. Once you've started doing it, you can't stop, and you have to try and keep it as current as you possibly can. So, that's something I need to get working on, really. Finally, importance of independent voice. Well, none of us are really independent, are we? Because we all receive our money from somebody who wants it for something. So I think that's quite a caveated and loaded sort of word to use. But there are other things around that we in BGS like to aim for. One of those is being trusted by pretty much anybody who wants geological information in this area. And the other one is perhaps being non-partisan. Okay, so we try to be non-partisan, and it's a tightrope because we do receive funding from industry, we do receive funding from other grant sources. If they could afford it, we would receive money from pressure groups. You know, we have to be non-partisan and work across all those bodies. Highlighting, you know, perhaps where we lie in that, a company might produce a resource estimate that is they have reasons for doing that. We might produce a resource estimate with a different kind of agenda, and the two are different. Both are equally valid, but our motivations perhaps are slightly different in those. So it's worthwhile for BGS to be in a position where we can produce a non-partisan review of this kind of information. And the same was the example for the scientific community as a whole when we were looking at seismicity in the northwest of England. This wasn't specifically a BGS thing, but you know, because of the way that seismic information is collected, you can't disguise the fact of when an earthquake happens and is coincident with hydraulic fracturing. So you know, we're in a position where we can all be quite open about how we would interpret that. And I think that's an important thing to, certainly in BGS terms, to remember. Going forward, I am running out of time very quickly, very soon. What we're going to do going forward, there are a couple of big projects you will have heard about. I'm going to tell you very briefly what I know about them. One is in the 2014 autumn statement, there was an announcement of 31 million of capital funding going into an energy security and innovation observing system, ESIOS, which will consist of 2 subsurface test sites in the UK. Okay, funded by Bayes, owned by NERC, delivered and operated by BGS as facilities. So that's what we will be setting up. Okay, hopefully operational by 2019. There will be one site in the northwest of England. Hopefully there will be one in Scotland as well. And they will be for all of you in the research community to utilise. Okay, there will be a programme of research funding provided by NERC at some point based on one of the, a research committee set up by NERC, and then there'll be a call for research. And basically BGS will be owning and running a laboratory where you will come and do some experiments should you be successful. And the laboratory will comprise some boreholes, network of sensors where we can do experiments, perhaps in areas of fluid flow, chemical reactions, subsurface linkages, etc., etc. And we'll see what the research calls look like when they come. The second initiative that we have starting is the National Geophysical Survey. So you will have seen I showed you that, I'm out of time, that fence diagram of the UK, and I said data is sparse. Well, we want to make an effort to actually get more subsurface data, and this is the way that we're doing it. So we've put a call out for parties who are interested in a survey to actually form a consortium and fund a survey, and we would effectively have the rights to use the information that comes back from it to improve our understanding of the geology. The ground rules of that are currently being established, but it will probably progress quite rapidly. I think I'll leave it there. Thank you very much. No time for questions.
David, thank you very much. Thank you very much for that very thorough presentation, actually. And you will get a chance to ask David questions this afternoon, because he's going to sit on the panel that will be down here as well. So you have some ideas. I'd like to move on straight away to the next presenter, Kevin Taylor from University of Manchester, Geological Processes and Characterisation of the UK Carboniferous
Thank you, Adrian.
Hodder Shale.
Thank you, Adrian. Okay, well, David's nicely set up some of the geology. I'll talk about some of the geology, including some of the interesting bits of geology. I should also say that, so I'm going to present some information today. Really, I was asked to give a general overview about some of the geology and why it's important. So I won't be giving too much information in detail. Some of the people on this list, so Anne is actually here. She's part of the project. She's got a poster in the coffee area. So please, some of the information I show on here is explored more in the poster. Sarah and Tim are actually PhD students who aren't involved with the project, but they're looking more broadly at the Bowland Shale. If you've got time after this meeting and hop on a train to Cambridge, you can join the annual conference networking event in Cambridge that they're talking about the Bowland Shale. So This is more of an overview, but and I should also say that BGS are involved. So Ed Hoff is working with us on some of the projects. So it's BGS involved as well, so it's a fundamental part. So what I want to do today really is very briefly, we were asked, as part of the project, WP3, part of it is fundamental geo-understanding of the characteristics of the rock, which then feed into work pages 4, 5, 6, 7, 8, etc. And one of them is also to feed into our own work, which is with Peter, particularly Peter Lee, who's talking later on about three-dimensional imaging and experimental 4D imaging. So in a way, it's providing the sort of bedrock. So I suppose I am giving the bread and butter type of work that goes into the project and then working with people on the more exciting aspects. Those of you who watch Big Bang Theory, I do believe geology is more interesting than Sheldon Cooper thinks it is. So I suppose the four things I wanted to focus on today really is to explain a little bit, a bit about the context of the rocks we've chosen to work on today, which is the Boland Shale. It's part of the project, which has been set up nicely already. Just very little bit about the variability. We're interested in how they vary, so we're interested in what drives variability regarding maybe the initial depositional processes, but I won't say too much because there's a lot of work in there which has been presented elsewhere, and we can talk about that at lunch if you're around. A little bit about the nature of the organic matter in these rocks and how that varies, because of course that's important for both producing organic gas and storing gas. The mineralogy, which is important for how the rock behaves, fractures of course, and how it may behave mechanically. A little bit about porosity types, but again we've got lots of data on that. It's developing 3D data at the moment, so this is a 2D talk in a way. And then something about the later chemical reactions which take place which modify the rock, so very briefly. So we've chosen, well, this is the background, basically, those of you who are familiar, the lower to middle Carboniferous, which is the Boland and Hodder Shale time, we were sort of equatorial at the time and on the end of this Eurasian platform, landmass. More specifically, of course, and this links into some of the, I'll stand here, links into some of the diagrams which David has showed, the sort of the geology of the Carboniferous play in the north of England is basically a number of these sort of smaller troughs around these emergent or semi-emergent hides. So we're looking at these smaller troughs, which is, if you remember the picture that David showed, these map onto the sort of, if you like, the resource estimates. They're in these sort of areas, the Boland Basin, Stainmore Trough, Gainsborough Trough. So the Boland Basin Trough, we've decided as part of the consortium to work on the Boland Shale for 2 or 3 reasons. Even though there's lots and lots of information out there for American, we can look at American cores, so the cows come home. We wanted a European active play version. We wanted something that had some core material available, so we were restricted to the Boland Basin to some extent, and we chose the most recent, we've chosen for the particular project we're working on with the consortium, we've chosen the Priest Hall core, which is the Cordilla core, which was released to the public about a year ago. But also, so that's over here in near Blackpool, and then we've also got, there's also, and Al might know, there's also some BP mineral cores about 30, 40 years ago now, which go through the same rocks over in this part of the basin over here, which is actually the other side of a fault system. It's actually an interbasinal high, so it's different than over here. So, but they're more continuous cores. The actual the Priest Hall core is actually not continuously cored. It's in sort of 3 or 4 chunks. And if you want to get some samples of that now, you probably missed the chance because it's been so heavily sampled now, it's almost gone. Just to give you a background again, so the Carboniferous, really, we've got 2 bodies which we're looking at, and this is depending how you deal with your local semantics, and geologists love naming things, formations members, and it changes from different basin to basin. But really, we're looking at the Boland Shale group and the underlying, what some people call the Worston Shale group, but other people call the Hodder Shale group. Depends where you're on the basin, depends who you are, depends on the biostrat. But technically, the Hodder Boland will be the lower Denantian up into the lower Namurian. It's upper Denantian, lower Namurian session. So there's a big thickness of these rocks. It's just the names, okay. So we basically we can date these rocks across basins. So we know the rocks we've got cores through. We know the age of the rocks based on the biostrat and the ammonoid assemblages. I think we've basically got 2 cores. We've got the MHD11 core, which is the one which the other project's working on. This is a project that Sarah's working on as part of a BGS joint project, which goes through the whole section, and also the Priest Hall goes through the whole section as well. But as I said before, it's basically dominantly cored in the lower Boland Shale, not much upper, a little bit in the Worston, but not an awful lot. So we've got a shorter section in here and a longer section we can compare it to. So really, one of the questions that our partners want to know was, what's the composition of the rocks? How does it vary? So we basically went to the core store and took loads of samples, various sizes, different measurements. And the idea is there's one sample set which will be used across some of these measurements. And actually, in the Priest Hall core, there's not that much variability. And you can break this down into many ways. It depends if you're a splitter or a lumper. But really, if you're a bit of a lumper, you can basically put, there's only 4 major sort of variability in that particular core, at least in the core that's cored. And that's some quartz-rich mudstones that are not laminated, some quartz-rich mudstones that are laminated. You can see some laminations here, which are primary sedimentary features. Some interlaminated quartz-rich, organic-rich, so quartz-rich with pyrite-rich layers, and then a carbonate-rich mudstone. And that's pretty much the variability. Not an awful lot of variability in that particular core. One of the questions that has come out when we looked at these is that quartz-rich, there actually are very quartz-rich, these rocks. And the quartz is there in 2 forms. It's there to trital grains, and it's there as a cement. And actually, most of them, not all of them, but most of them are fairly clay poor, 10, 15% max clays. And that's not unusual for some of the American shales. Although they're shales, they haven't got to be clay rich. That's not part of the deal. Shales can be quartz rich and clay poor, and these actually are quartz rich and clay poor, which probably is a reason for why they fracture quite nicely. Alberto showed at the start. If we look at the other core, just for comparison, because we've really done basic characterization work on this. It's really basically bread and butter work. We've done more work on the Mile Hill core, which will then be move on to this as part of the next project for Sarah. Is actually in the Mile Hill, which is slightly more. It's slightly to its interbasal high. It's not got such deep water. Basically, it's got similar variability. It's got some. I can't read either of this. It's got some calcareous clay stones, some calcareous mudstones, so some clay-rich. There's actually some more clay-rich material in that part of the basin. There's calcareous mudstones, and again, argillaceous mudstone. But again, they're fairly. The variability isn't enormous. If you're interested in composition, there's not a lot of variability. It's mainly in the sort of fine descriptions. But the key point what we find is that these rocks, this is one of the things I want to bash home, though it's not necessarily important for people doing mechanical tests, for example, is that these rocks are all very dynamic. They're either distal turbidites or they're debris flow deposits, distal end off. They're very dynamic. They're not settling out the water column like this. They're basically pulses of sediment coming in from the basin margin, fine-grained material coming in as either aggregates or as clay particles coming in and forming all manner of small little cross-bedded turbidites, etc. So a very dynamic system, and that helps us to start thinking about how the rocks change around the basin. But of course, that's part of a bigger project, and that's linked into understanding resource assessments and where organic matter might be preferentially preserved and deposited, which gives you the better source rocks and the better shale gas reservoirs. And again, similar things, but again, all these 6 fascias you show normally graded beds with erosive bases and waning intensity flow. They're all very dynamic systems. So, but again, the message to take home really is that the variability is mostly in subtleties of clay content versus quartz content, apart from the occasional unit that's heavily cemented with a cement, and obviously it's very different. So that's the first thing. The variability is small, but there is some, and that will affect some of the properties depending on what you're measuring. One of the things that's interesting, we note time and time again, and I'm going to say this as a geologist, is that actually these rocks contain this lenticular fabric. And I'm not going to, the slide's a bit detailed. The bottom line is the rocks contain pieces of existing clay, existing rock fragments, or other types of material that's been ripped up from elsewhere in the basin and moved into the centre of the basin. So again, it's a very dynamic system. So for understanding where the best source rocks will be, we need to understand this bit more. So this is something that's probably beyond the scope of this particular project, but it links into the project's understanding the regional play variability. What about organic matter? Well, we saw a picture of some amorphous organic matters. Now, these are images that Anne's been working on the Priest Hall core, looking at the organic matter variability types. And there's actually four types of organic matter you can recognise in these rocks using SEM observations, etc. We've got organic matter without sort of maceroles like this, without micropores, and organic matter with micropores. So we see organic matter maceroles that contain that don't have porosity, and we see some that have this very abundant intra-organic porosity. And of course, classically, people think that's where a lot of the gas is held, in these micropores or nanopores. But we see both types, and actually It may well be that the macerols have got different types of composition. That could be vitrinite versus inertinite, for example, etc. We have a girl starting to do some Raman spectroscopy on these with limited success, trying to distinguish the composition of these things. It's actually very hard to see a difference. So, but something controlling the difference in organic matter types between no pores to pores. But also organic matter it occurs in these sort of interlaminated clays and quartz and organic material. It contains a small particles inside here, but also particularly it's the OM4 is these things are called oversized pores. And actually, we believe, and I now believe, these are probably migrated bitumen. And actually, look at some of the US classic plays. Lots of the organic matter which hosts the gas is actually not macerals organic matter. They're actually bitumen. And we'll come back to that in a minute. But bitumen, there's been some migration of oil in these systems before subsequent cracking and formation of porosity. So organic matter variability is very variable, and it's variable on even on one thin section or one grain area of a slide here. So clearly, understanding the variability for across the basin is a challenge. But in the rocks we're looking at, it's quite variable. So if you're interested in understanding organic matter activity with fluids, for example, or with chemicals, it is very variable. But there are other pores in these rocks and other minerals. Two things that come through is that the porosity is not limited just to the organic pores. We do have intercrystalline pores, for example, here. These black areas here are pores that are between mineral cements. Again, you can see a nice pyrite framboid. Again, there's porosity between those. So the porosity in these rocks is not limited to the organics. And so that means your gas will behave differently in the different pores. So there'll be pores that have got maybe some absorbed to organic material, but there'll be some inorganic pores where you don't have absorption capacity and it's just free gas fully. So we need to be aware of that. And this was some of the three-dimensional work we started to do. How are these 3D, are they connected differently than the organics? We think they are. Then the other thing that's truly amazing about these rocks is there's been a massive overprinting of a mineral phase that's actually changed the initial fabric, changed the texture from what it was initially. So we've got predominantly kaolite, calcites, dolomites, and quartz cements are abundant in these rocks. And so you can see here an example. This is basically a part of the rock that's been totally changed by chemical reactions. So understanding the different types of mineral reactions helps understand the variability. Because some of these minerals preserve porosity, some create porosity, some of these obviously create rigidity and brittleness to the rock. So understanding which minerals are where will help us understand which bits of the rock are more brittle. These here have got more clay minerals. You can see some clay, some sort of bits of mica here that have come into the system. But again, all the rock, the dolomites, the pyrite, it's all orthogenic rock that's overprinted that particular texture. So the next step is to try and understand what controls the different pores and how they are controlled and how they time differently in the rock. So we can then feed into the partners to say, well, in these rock samples, you've got this type of material dominated by this process, which gave rise to these pore types, X, Y, and Z, in these connectivity, X, Y, and Z, etc. And then lastly, just show some more of these complex relationships. We've got these overprinted anchorite, dolomite, rhombs, calcite, quartz, cement. You can see nicely this is quartz cement, overgrowths, clays. This is kaolite. Again, totally orthogenic. It's not detrital. It's come in the system, precipitated at burial depths. Chlorites, altered albites. The whole thing has gone through enormous chemical changes. Now, one reason why that's the case, and this is the fourth point we're trying to get to, just before I run out of time, is the whole, not all of it, but a lot of it, if you look at particularly both Priest Hill core and in the Mile Hill cores, and other cores you can see for Boland, there's been intense fracturing and vein filling generations. So you can see here you've got the minerals that have been fractured, and then there's been these vein fills come through of a different mineral phase that's basically completely overprinted this rock. And it illustrates the rock as both fractured, but also fluids that move through the system. So try and understand how those fractures are present, and particularly which ones might be giving rise to weaknesses in the rock and plains is obviously an interesting question, because there's also that lifelong debate about, are fractures helping you frack a rock, or are they making it harder to frack a rock, depending if they're filled or open. So again, Anne has got, on a post, you can talk to her, Anne has recognised four, from thin section and SEM work, recognised 4 vein generations. So there's a fracture vein 1, which is basically a calcite, sealed fractures, so these have opened up and they've been filled in by a calcite, mineral cement. not just calcite, some dolomite as well. Then there's a fracture 2 system, which is basically bitumen. We've got these bitumen veins that cross-cut minerals. We know we can time them. So there's an earlier phase of calcite, there's a later phase of bitumen, which cross-cut some of the calcite veins, cross-cut some of the earlier cements. We know where they date in systems. But they must post-date ore generation because there's bitumen in those veins. And then we have an F3 fracture, which is actually open fractures, which go through the quartz and the calcite cements. Now, these, of course, could well be an artifact of preparation, an artifact of drilling and coring, bringing to the surface. So these are less clear at this time. Unlikely to be open at depth, but they're very, I mean, it seems to me unlikely that you can get a fracture through a quartz grain just by making a thin section. So there's something going on here that maybe these are actually fractures in the surface, closed up but present. And then also there's obvious, what we think are obvious fractures opening up much smaller as a result of the fact it's at the surface now and the pressure's been released. So you get a lot of these interfacial, what we call interfacial pores even, and again, obviously they're very common in these rocks around minerals, but again, we think these are dominantly a result of pressure release during uplift and obviously brought to the surface. Illustrates the complexity of understanding these pores and cracks when you haven't got the rock at its burial pressure. You bring it to the surface. So that's an overview of the sort of things we're trying to understand and why. We're understanding what the variability is and why that's driven. Is it depositional? Is it chemical diagenesis? We're trying to understand the porosity types in the rock, understand organic types, because organic types obviously give rise to the porosity types sometimes, also give rise to the organic richness, and also trying to understand the fracture networks in some of these very deeply buried or tectonically modified shale systems to understand what their fracture generations are. So I've just a sort of summary really, but pretty much what I've said really. And these are actually the BP mineral cores. These are actually ones from this is actually some of the carbonate rocks. So if you look at the general rule of thumb in the Bowden Shale is that the earlier ones are dominated by carbonate-rich mudstones, the later ones dominated by quartz-rich mudstones, and the most late ones dominated by clay-rich mudstones. That's generally the pattern you see in the basin we're in anyhow. Okay, that's a summary really. I've gone amber, so done. Right. I'll be around for questions. You want to move on or you can ask questions now?
Can I ask a question?
Yeah, okay.
Just a quick one related to the horse structures. A non-technical explanation for that.
I might throw it straight to Al.
Yeah.
As the expert of the basin.
What, the fault blocks? The fault blocks.
Al is the expert who did the original work with Fraser and Gawthorpe. Fraser and Gawthorpe, famous, and you have the man here. Ask Al.
Just a very brief
Not correct him.
No.
No.
Just a very brief explanation for what the fault blocks are caused by.
Yep, that's on. Al Fraser, Imperial College. Yeah, the fault blocks are formed as footwalls to the half graben which contain the Boland shales. The half graben are roughly about 10 to 20 kilometres wide. They are based on reactivation of underlying Caledonian lineaments, which were originally developed during a compressional orogeny. So it's reactivation of a basement fabric. Some of the fault blocks are underpinned by Caledonian granites, which keeps and maintains their elevation as well, but not all of them. So it's a fabric of elevated footwalls and subsiding basins.
Thank you very much. That's very helpful, thank you.
The point is, of course, is we showed they are very, they're much smaller basins than in the US, but they're much thicker. Well, some of them have got much thicker successions in the US. Not all of them, of course.
Those rocks are very consistent in quality.
Thank you.
No worries.
Thank you, move on. Thank you very much, Kevin, and thank you for your input, Al, too. Next, I'd like to invite James Verdon. Hydraulic fracturing, microseismic monitoring, and induced seismicity. You just talk to this one.
Sure. Okay, thank you very much. Just to very briefly introduce who I'm sort of representing when I talk to you today. We are BUMPS, or the Bristol University Microseismicity Project. We are a industry-funded research consortium. We have about 10 industrial sponsors, both operators and service providers. We've been around since about 2005, so I hate to sound too much like a hipster, but we were working on shale gas and hydraulic fracturing long before it was cool. But our particular focus is on, as you say, microseismicity. And when we first started the research consortium, we were very much focused on using microseismicity to kind of optimize the hydraulic fracturing process, to optimize fracture placement, well spacing, etc. In the last few years, the focus very much coming from our sponsors, the operators and service providers, has been much more towards, understanding induced seismicity and fault reactivation. Why does it happen, and what steps can we take to try and mitigate against it? That's recognizing that this issue has become, in the last few years, much more of a significant issue than it was during the early stages of shale gas development. So a very brief outline about what I'm going to talk about. A very quick motivation. It should be fairly self-explanatory, but there are a few little details about why do we want to avoid induced seismicity and fault reactivation beyond the obvious ones. And a very quick introduction to what is microseismicity, microseismic monitoring, just in case for those that aren't that familiar with it. I'm going to briefly introduce the state-of-the-art microseismic data sets that we're working with, and then use those data sets to try and address a couple of key questions, namely, A, how can we differentiate between when faults are being reactivated and differentiate that from what you might call sort of normal hydraulic fracture? I mean, hydraulic fractures can vary very much from basin to basin and play to play, but sort of the normal hydraulic fracturing versus fault reactivation, and then to try and address, okay, what mechanisms are causing this fault reactivation? How do we understand how hydraulic fractures and faults intersect with each other and interact? And then obviously to close with a few discussions and conclusions. So the motivation, why would an operator want to avoid fault reactivation and triggering induced seismicity? Well, the obvious one is if you cause large events, you potentially damage local buildings and infrastructure, and obviously you're held to account for that. But even a lot of the comments you might get from some operators, well, these are only small events. Some of these smaller events are not really large enough to actually cause any damage. But obviously, if they're large enough for local populations to feel, then even if they're not large enough to cause damage, that it's going to cause loss. You're probably going to have regulators putting increased burdens on you. You're going to have reputational damage, and obviously you're going to find local opposition. I mean, we've seen in the UK one small magnitude 2.3 event in 2011, and since then we've had 5 years and no one's been able to perform a single hydraulic fracture stimulation. So even small events, can cause big issues, with the public, for example. And then the second half is actually that, forget about any of these issues. It simply can represent inefficient hydraulic fracturing for the operator, because you spent money getting your hydraulic fracturing fluids and pumping it down your well. If all it's doing is then just flowing into a pre-existing fault and it's not actually breaking apart shale rocks to produce gas, then you're effectively wasting time and money. And also, a particular problem in some of the shale plays in the US has been that if your fault propagates down into non-hydrocarbon-bearing layers underneath your reservoir, then when you begin to produce those wells, you've got a flow pathway from saltwater-bearing layers into your well, and you get increased water production, which is obviously less efficient gas production. So there are many reasons why you'd want to avoid triggering fault reactivation and induced seismicity during hydraulic fracturing. So a quick introduction to what is microseismic data. I think it's best represented by the image. You place geophones in monitoring boreholes around the zone that you're going to be stimulating, and you record the seismic emissions that are produced as the hydraulic fractures propagate through the rock. So, as hydraulic fractures propagate, you've got fractures being opened and reactivated. That process releases seismic energy. You pick that seismic energy with the geophones, and then you use techniques derived from conventional seismology to locate where that energy is coming from, which then you use to tell you where the hydraulic fracturing is propagating. And it's used for a number of reasons, to track your hydraulic fracture propagation, which you then use to optimize your drilling and completion strategies. You might, for example, identify barriers to fracture propagation. Fractures are going through certain layers, they're not going through certain other layers. You might use it, for instance, to calibrate discrete fracture network models that you then use to simulate production. And what we're particularly interested in is to identify when and where your hydraulic fractures have intersected faults and might pose a potential environmental or just optimization of fractures hazard. So a quick introduction to the data sets. I'm not at liberty to say exactly where these come from, but from North America. These are large, multi-well, multilateral stimulation projects. So you can see 10 or so wells. maybe 20 or 30 stages per well, and recorded with sort of 3 arrays of downhole geophones, which are marked by these red triangles here. So these 3 monitoring wells, picking up something like 100,000 events overall, so that's something like 1,000 events per fracturing stage. Magnitudes ranging from -2, the smallest events, through to magnitude 1.3, the larger events. And there's clear evidence for fault reactivation. That should be apparent from the cross-section here. So you can see the wells coming down here. All the events that are around the wells, that's probably normal hydraulic fracturing. But you see at this section here, these events that suddenly propagate, several hundred meters below the stimulated target interval, and they're kind of a sort of planar structure to it, and that's pretty clearly fault reactivation. Again, a second data set here, same sort of thing. We have these multilateral wells, multi-stage simulation, and again, you can see sort of 3 planar structures propagating down several hundred meters below the target interval, which is almost certainly fault reactivation. So beyond simply by eye, the first question we want to ask is how can we differentiate, quickly and uncontroversially between fault reactivation and the normal hydraulic fracturing process. And the way we're going to do that is by using this parameter, which is the Gutenberg-Richter B-value. So for those of you who don't have the good fortune to be seismologists, I should quickly introduce what the B-value is. When you plot up the number of events versus their magnitude, they tend to fall along a straight line, sort of in log space, in a sort of power law distribution. And the B-value is the gradient of that line. So these are 2 just completely made-up synthetic distributions. They release the same amount of seismic energy overall. The area under these 2 lines is the same, but you see the slope of the lines is different. And so a higher B-value means a higher slope, which means more small events, fewer large events. A lower B-value means a shallower slope, which means fewer small events and more large events. So when you look around the world at sort of regular, normal tectonic seismicity, our normal earthquakes, they follow almost exactly a B-value of 1, and that very rarely changes. That's just kind of the Gutenberg-Richter law, as it's referred to in seismology. However, in certain situations, in places like volcanoes, where the seismicity might be being triggered by pressurized fluids, you've got a lot of hydrothermal fluid and magma in volcanic settings, for example, we see B-values elevating to values larger than 2. So the suggestion is, for the same thing during hydraulic fracturing, where you've got seismicity being induced by, or where you've got sort of normal hydraulic fracturing microseismicity, you should have high B-values. Where you start to reactivate pre-existing faults, your B-value should drop to closer to 1. So going back to that data set, I've simply plotted up all the B-value distributions, so magnitude versus number of events again. And I've coloured the population because there's very 2 distinct populations. The vast majority of stages, very steep slopes here, high B-values, generally larger than 2. But there were 5 stages shown here where the slope was much more shallow, B-value closer to 1. And it really was quite a clear difference between these event populations with this slope and these event populations with this much steeper slope. So we're going to suggest that these are the fault reactivation stages as imaged by the low B-values, as opposed to normal hydraulic fracturing, which for most of the stages has a high B-value. And just to show what happens when you just look at those clusters with low B-values. So this is all the events. We zoomed in on this area now. We're going to zoom in on this area here. When we look at those low B-value stages only, so looking just at the low B-value stages, this is what we pull out. So this is all the events. So this is all the normal hydraulic fracturing that's going on. When we just pull out the low B-value stages, the geometry of the faults suddenly becomes very clear. We see 2 planar structures, sort of 2 antithetic faults here, and then a third fault sort of slightly over here as well. So, by using those B-values to pull out the clusters where you have low B-values, we're able to image the faults very clearly using the microseismic data. And just a map view as well. There's all the seismicity from the stages we're interested in